Hi class, welcome to Refrigeration and Air Conditioning lecture number 6. In this lecture we will be exploring thermodynamic principles that are relevant to refrigeration with the help of the CoolProp software. So what exactly is thermodynamics? It's the science that deals with transformation of energy, particularly particularly the relationships between heat, work, internal energy, enthalpy, etc., other forms of energy. So it helps us to provide a framework on understanding the energy transfer processes, and also the primary purpose is to understand the efficiency of the process that is used for a particular application. There are essentially four laws of thermodynamics. In this particular lecture, we'll focus on the zeroth law and the first law. So we'll introduce these two laws and we'll try to understand a little bit about them using CoolProp calculations. We'll also look at a lot of properties also using the CoolProp software. Now, the first thing to do here is learn some basic terminology, okay, the terminology that is typically used in thermodynamics. So the first one is a system. You're familiar with the thermodynamic system, but still we'll do this as a refresher course. So a thermodynamic system is basically a region or a group of matter or a quantity of matter that is um, that can be considered to be together, and it's separated from its surroundings by an imaginary or a real boundary. Okay. Now, in some systems, there could be energy transfer across the boundary, and in some systems, there could be matter transfer. In some systems, there could be no transfer of energy or matter. So, based on this, we have three types of systems: the open, the closed, and isolated. Now, this boundary could be fixed or movable. Okay, it could be real or imaginary, it could be fixed or movable. We can understand that as we go through these examples. So let's start with an open system. An open system, which is usually referred to as an open system in thermodynamics, in fluid mechanics, such a system is typically referred to as a control volume. Okay, so basically, both matter and energy can cross the system's boundary, and this is what happens most of the time in real systems. Okay, so if you look at the cup of coffee here, and you look at the system boundary that's drawn here, you can see there is heat being transferred because the coffee cools in a warm and a warm coffee will cool when it's left in a cold environment, colder than the coffee, and it will eventually reach the temperature of the surroundings. Okay, so there is definitely energy transfer across the boundary. You will also notice steam leaving the coffee cup, especially when the coffee is really hot. So there is essentially transfer of mass. A lot of water vapor is leaving the system, right? So there is both a mass transfer and an energy transfer in the system if we consider the system to be basically enclosed by this cup and by this dotted line. Now consider a closed system. Okay, so imagine an unopened sealed bottle of water. So in this case, there is no water leaking. Essentially, we could say that there's no mass that is leaving the system. And we have a real boundary. You don't have to imagine it. You could just consider the outside of the bottle as the boundary, okay, including the cap. I should have drawn it this way. Okay, so you have a real boundary and there is no mass that's leaving the system. But if you put this water bottle in a refrigerator, it will cool down. So what that means is energy left the system and it became cold. If you put this in a microwave, heat will go in and it will warm up, right? If you left it in the sun, it will heat up and the water's temperature will increase. But there is no change in the mass. And depending on heating or cooling, the volume of the system, the boundary of the system could also change. Okay, so those plastic bottle could expand or contract. So the boundary could move. It doesn't have to be fixed. Okay, but at the same time, there was no exchange of mass. So this is also happens in real systems, even though not as common as the open systems or control volumes. There are still a lot of real systems that fall under the category of closed system. They're also known as control mass. This one is known as control volume, the open system. You could refer a closed system as a control mass because there's no change in mass. An isolated system is actually a very idealized system. It doesn't really happen in real life, but there are some systems that come really close to it. A good example is an insulated thermos flask, okay? A vacuum insulated flask like this. So you have a vacuum insulated flask where energy transfer is really low, okay? It's not zero, but really close to zero. It takes a long time for energy transfer. And of course, if you seal the cup really well, seal the flask really well, there is no mass transfer. So such systems could be considered as an isolated system for some analysis, especially if you're not considering a long duration of time. So these kind of cups typically can hold a hot fluid hot for 16 to 18 or sometimes even 24 hours. So if you're only considering a matter of a few minutes or a few seconds, you could consider it as an isolated system. Okay, because in that situation, the energy transfer is really low. All right. The next aspect of thermodynamics is, or the terminology that you should learn is about thermodynamic state and also about thermodynamic property. And they have to be defined almost simultaneously. A thermodynamic state refers to the condition of a system that we just defined. Okay, so what condition is the system at? That's the state of the thermodynamic system. That's basically what is referred to as state. Now, how do you define that condition? It's based on the properties. So, thermodynamic properties define the thermodynamic state or the condition of that system. And once you know the condition of the system, you can understand what that system is capable of. Okay, so how much energy is present in that system? How much energy can you extract out of that system? So you can basically have a rating of that system. Okay, so thermodynamic properties are basically measurable or calculable. So this is important. Sometimes you can measure them directly using sensors. Okay, and sometimes you cannot measure them. You measure some property and then based on those properties calculate them based on some relationships. Okay, um, so there are two types in that sense. They're also called as state functions because it's only dependent on the state. The values only depend on the current state of the system, okay, and not on the path taken. And I will uh, explain this in the next slide. There are two different types of properties. One is basically independent of the size or mass of the system. So if you're talking about a bottle of water and then let's say there's a thermodynamic property, if the size of the bottle does not affect that thermodynamic property, then it's called an intensive property. Okay. And if the other way, if the system size or mass affects the property, then it's called an extensive property. So what are some examples of intensive and extensive properties? Pressure, okay, temperature. So imagine you have a small system inside this big system, okay? So the pressure here is some value P1. So if you took a bigger, larger size also within the same system, the pressure is still again P1, okay? Same thing goes to temperature, T1, T1. I'm assuming that it's already in steady state. There's no temperature differences within this, okay? So such properties that doesn't get affected by the size or the number of molecules within the boundary of the system are called intensive properties. The same thing goes for density, okay? Density of water in this water bottle at this location is same as the one at this location. So that's an intensive property, okay? Other examples are specific volume, which is the inverse of density and specific enthalpy. And we will discuss what enthalpy is. Even though you would have learned about it in the previous lectures, we'll do some basic refresher course on it later in this lecture. Extensive properties is dependent on the system size of mass, volume. Okay, so clearly, if you take a smaller volume and a bigger volume, there's a difference in volume. So it is dependent on the number of molecules or the number or the size of the system boundary. So volume is an example, mass, entropy, internal energy, total energy in there, all of that is dependent on the size of the system. Now, how many properties are needed to define a state of a system? Okay. For a simple compressible system, basically a pure fluid, two independent intensive properties are sufficient to define a thermodynamic state. Okay. So if you remember in the previous lecture, we had talked about two inputs to the props SI function. So if you remember, there are two inputs, okay, for example, pressure or temperature, and let's say you want an output of density. Remember, so those two inputs are two independent intensive properties, and they will define the thermodynamic state. And once you know the thermodynamic state, you basically know the condition of the system. You know all the other properties, all the other thermodynamic properties based on that particular state. And how do they achieve that? So basically, these two properties determine all the other properties through a system's equation of state. Okay. And again, this is for a pure fluid. If it's a mixture, you will need more than two properties. Okay. If it's a mixture of two pure fluids, you need more information. For example, you'll need the information on the mixing ratio in addition to the pressure and temperature. Okay. So pressure is an independent property and temperature is an independent property. So together they can define the system. Pressure and density also can define that system. Temperature and specific volume, pressure and specific volume, all of those can define that system. Okay. All right. Now, we mentioned earlier that property is a state function, right? That it only depends on the current state of the system and not on the path taken to reach that state. So what we basically are saying is, um, so let's say you have a bottle of water here, okay? Instead of a bottle of water, let's say there's a bottle of gas, okay? So, and that's at a particular state, state number 5. So you have a bottle of gas in state number 5. It has a particular pressure, and in this case, it's volume, specific volume, okay? Let's call it specific volume. Now, the thing to note here is, I forgot to mention this, specific volume is an intensive property, but volume is not an intensive property. So I assume you already know the difference. Specific volume is volume per unit mass, right? So it's basically it's inverse of density, right? Volume is basically volume. volume per mass does not change because the density of the substance doesn't change. If it is water, water's density typically is 1000 kilogram per meter cube, right? So you could say its specific volume is 0.001, which is inverse of this meter cube per kilogram. So typically, if you look at this bottle and assume that that's the density of water, so the specific volume will not change. It will be 0.001 kilogram per meter cube. But the volume definitely changes. Sorry, 0.001 meter cube per kilogram. The volume definitely changes depending on how you select the boundary. Now, what I want you to take away from this is if there is a property and that property is a specific property, right? There is a specific term in front of it. Usually that means it's per mass or per mole or per volume, things like that. When you do that, you typically are accounting for um, the um, the mass specific property or a quantity specific property. So then it becomes independent of the size of the system. So whenever you see specific term in front of a property, it is an intensive property. Okay, so something to keep in mind. All right. Anyway, so in this case, let's assume this is specific volume. Okay, so it's basically meter cube per kilogram. And to determine the um, the property of to determine the state of the system, you need independent intensive properties. That's one of the reasons I changed this to meter cube per kilogram, because now this is an intensive property. Volume would have been a um, extensive property. So if you have two independent intensive properties, you know the state of the system anywhere um, within that phase diagram or the property diagram. So in this case, let's say it has a particular pressure and a specific volume. It doesn't matter how you got there. So it will have a corresponding temperature, density, all of that. Okay. So it doesn't matter if it came from 2 to 5 or 1 to 5 or 3 to 5. Like, how did you get from this condition to this condition? It came from here to here. It doesn't matter. We will not know how it got here. When we measure the pressure and the specific volume, all we know is the state of that system. Whether it was compressed isobarically or isothermally or adiabatically or isochorically, you will not know because there's no way to tell. So such a property is called state function. So all thermodynamic properties are state functions. Okay, only depend on its current state, not the path taken to reach that state or the previous state. Okay, um, there are some terms in thermodynamics that are path dependent. Okay, so we will get to those later. Like for example, things like heat and work, all of those that are path dependent. Okay, all right. As we had touched upon earlier, thermodynamic properties could also be defined as based on whether they are measured or calculated. Measured versus calculated. So if it is directly measured, it could be directly measured using some kind of sensor or device. They are typically known as primary properties. And if they are derived properties, which are calculated from primary properties using the equation of state, they are called derived properties. And here is a list of the common thermodynamic properties and the symbols that are typically used, their units, and their type. Okay, so some of them are in the intensive versus extensive category, and then some of them are in the primary versus derived. There are primarily four primary properties: pressure, temperature, volume, and mass. You can measure pressure with a pressure sensor, temperature with a temperature sensor. Volume also can be measured using scales and other volume estimating methods. Mass can be estimated using a weight sensor. Density is calculated using mass and volume. Okay, so it's a derived property. Internal energy, a lot of times you use temperature, pressure, and equation of states to calculate internal energy. Specific volume is just like density, it's the inverse of density. Enthalpy, entropy, all of these, again, it has temperature and pressure dependence. Same goes for specific heat, capacity, at constant pressure and constant volume. A lot of these properties, all of them could be derived using pressure and temperature, or at least two independent intensive properties. Okay, and you have to remember the that any specific property will always be intensive because it has a per kilogram or per mass feature that makes it independent of mass. Okay, all right. Now let's go to the thermodynamic laws. And the first law of thermodynamics is the zeroth law. Okay, so the zeroth law basically is the law that defines thermal equilibrium. Okay, so what does thermal equilibrium here mean? If two bodies are to be in thermal equilibrium, what that means is there is no um, temperature difference between them. Okay, so if they're in contact or not in contact, if they're in if there's a radiational heat transfer happening, but the temperatures have equalized and they're same the temperatures are equal, then there is no effective heat transfer between them. They're in thermal equilibrium. Okay, so this is the principle that is used for measuring temperatures. So if you want to know a body's temperature, what do you do normally? You use a thermocouple or a thermometer, and you measure the temperature of that body, right? So the assumption is after it reaches a certain value, it, there's no more change because now this temperature is same as this temperature, and there's no more change beyond that point. So they're in thermal equilibrium. So the actual law is a little bit different from what I just stated. It states that if two bodies are in thermal equilibrium, and one of them is in thermal equilibrium with a third one, then the third one is in thermal equilibrium with the first one. Okay, so essentially they are all at the same temperature. So that's a simple law uh, to define thermal equilibrium. Before we get to the first law from the zeroth law, we have to define multiple properties. We have to define energy and all that, and um, we'll do that in the subsequent slides. Okay, so let's start with specific volume. Specific volume is a thermodynamic property that represents the inverse of density, right? And we will try to see how to calculate specific volume using CoolProp's SI. Okay, so these are the units in SI, and let's open up the Excel file um, that has been shared with you. So here, it's a simple equation for density, okay? And 1 over density is what the specific volume is. In CoolProp, there is no specific volume property uh, for pure substances. Okay, so here you calculate the density and then do the 1 over density. Now I have done this for single phase like air and nitrogen, and I've also done it for the single phase of substances like water for both gas and liquid phases. Okay, so how did I do that? So what we can do is, in case of a two-phase substance like water or a refrigerant, you find the saturation curve, right? Okay, so you pick let's say you pick, let's say you picked a point here. Now, if you want the properties of a liquid, what you have to do is you have to find this particular pressure and temperature, and you can increase the pressure from that point to get the liquid's properties. And you can decrease the pressure to get the properties of a gas. Okay. Um, so that's what I've done here. So for a given temperature, I calculate the saturation pressure using the saturation pressure equation. And like I have explained in the class before, if you use the quality Q function here, that means you're looking at the saturation line. Okay, so you're looking at saturation properties. So using this, you get the saturation pressure in Pascal of water at 25 degrees C. And then um, I subtracted 100 psi, 100 pascals from that to get a pressure below the saturation pressure. Now, if I use this new pressure, okay, this new pressure and this new temperature, I should get the properties of a vapor, okay? And I calculate the density, and the density is 0.0223. Now I add 100 pascals, so I will be in the liquid region. In that case, the density is high. So you can see that the density is different in these two scenarios, right? So 1 over that is a specific volume. So specific volume of gas is really high, of that of liquid is really low. You can verify the state of the fluid using the phase SI function. Okay, it clearly says this is gas under these properties, this particular temperature and this particular pressure, and it's a liquid under these two conditions. Okay, now I've done that for R134A2, so you can see the density and the specific volume of both liquid and gas of this R134A. So most of the gases that you see around you are supercritical gases. They are much higher. They're under much higher temperatures than their critical temperature. Okay, so their state will be a supercritical gas. So in this case, we are calculating helium's specific volume under several different temperatures. Here we are not looking at a saturation pressure. Here we have to provide two things. One, the temperature and the pressure, not the saturation pressure, but the pressure at which the gas is. So if you assume they are at atmospheric pressure, these are the specific volumes, right? And the same way for air, using the temperatures and atmospheric pressure, this is how the density varies. You can see as the temperature increases, density decreases for all of these, right? Okay, so that is very simple, calculating um, specific volume with CoolProp by indirectly estimating it, taking the inverse of the density. The next property is quality. Okay, so it is the, as we had discussed in the class, it is the property that defines the proportion of a two-phase mixture. Okay, so the vapor phase mass divided by the total mass of the fluid. In other words, mass of the vapor divided by the total mass of vapor and liquid together. Ideally, it is represented by the symbol X, but in CoolProp, as you already know, it's represented by the symbol Q. Don't get confused this with heat. Later on, we will use Q to define um, heat and energy conservation. But in CoolProp, Q means quality, okay? And it means this. Now, if you know the specific property of the liquid and the gas at, at a saturation point, So Q basically has meaning only primarily only on the saturation curve. Okay, if you're inside the curve, it's always 0. If it's outside the curve, it's always 1. Okay, on the curve, it could be anywhere from 0 to 1. Okay, so on the curve, basically, it means that it's similar to a box with some fluid and the remaining vapor. Okay, so depending on this mass of the fluid and the mass of the vapor, you get some quality number. If you're outside this, basically it's all vapor. Okay, quality is always 1. Because it's always 1 at that point, it's not used for calculations. At that point, you directly use whatever the pressure is and the temperature. But if it is here, its quality is always 0. Again, it's fully liquid. So the saturation properties are not valid anymore. So coming back to the equation for quality, you can calculate it directly like this, but for some reason, let's say you already know the individual properties, specific properties of the liquid phase. Okay, let's say they are in equilibrium. So if you know the some specific property y of the liquid phase and of the gas phase, and also the overall value, then you could use that to estimate the quality in a reverse method. Okay, so this is the equation for that. Okay, and by specific property, what I mean is there is a per kilogram per mass um, term there. So specific volume would be volume per kilogram, right? So that's a specific property. Specific enthalpy is enthalpy per kilogram per mass. Specific internal energy is internal energy per kilogram. So if you have any property like that, value y, you can estimate the quality x using this equation. You can derive this by assuming um, the relationship between the specific property and the extensive property. So if y is a specific property of the extensive property y, then basically it's related by m vapor plus m liquid, right? So y is the total specific property of the mixture, and capital Y is the extensive property, then it's related like this. Same way, the Y vapor and Y liquid will be correspondingly related like this, right? Y liquid will be Y liquid by M liquid. So if you substitute these, you can derive the same equation yourself. Okay. All right. So let's look at this in CoolProp. So go to the Quality tab. Here, what I've done is I've given you conditions for saturation conditions for water and R134A refrigerant at different temperatures. So we have a temperature, then we have a saturation pressure, and then we have uh, calculated the specific volume of gas by choosing Q is 1. So you're looking at density D, okay? And then you're taking 1 over that density for this particular temperature, and you're doing the calculation for gas. You do the same thing for liquid by changing this Q value to 0, okay? So you have the density of the gas, sorry, the 1 over density of the gas and 1 over density of the liquid. So you have the Vg and Vl values of the um, corresponding saturation liquid and gas. And now you can choose some random uh, value in between for the two-phase mixture. Okay, so the specific volume of gas is this much and specific volume of um, the liquid is this much. If you pick some value in between, now that means there is some kind of mixing between the gas and liquid, okay, because this value is between these two. How much mixing is there? You can calculate using the formula where the output is Q now, input is the temperature because we are using the same temperature, and the other input is this new mixture density, okay? So if you put in that mixture's density, you get the quality of that mixture. You can also calculate it based on the equation I just told you about. Use this particular equation, x equals the equation relationship between specific properties, and in this case we will use specific volume relationship, okay? In our case, y is specific volume. You can back calculate that using this formula and gives you the same number as the direct formula from CoolProp, okay? All right, so that's very interesting. And you could use this later on in some calculations when you know some properties directly from the phase diagram. You can estimate the quality. All right, going back to the slides. So we looked at two additional properties, quality and specific volume. The remaining properties like internal energy, enthalpy, um, latent heat, specific heat, all of that would need us to learn a little bit more about energy. Okay, so before we jump into calculating all those things in CoolProp, let's go through some basic understanding of the types of energy. So what is energy? Energy can exist, and in this case, we are talking about energy of a system. Okay, energy can exist in numerous forms as thermal, mechanical, kinetic, potential, electric, magnetic, chemical, nuclear, um, a lot of different types of energy, and you've heard about a lot of them one way or the other. If you combine all of them that are present in a system, then you get the total energy E of the system. Okay. Total energy E of the system per unit mass basis is just denoted by a small e. So this is almost like specific energy. Okay, is E divided by m. Now it's hard to find what is the absolute value of total energy. Okay, it's in a system. What thermodynamic provides is helps you estimate a change, okay, change of the total energy. Typically, the way they assign an absolute value is by choosing a reference point, a reference state, okay, a reference state, for example, of pressure and temperature. They will choose different states for different systems, and you can say for this particular gas, the reference state is this pressure and this temperature, and at that condition, you could assign a value of 0 to the energy, to the total energy. Now, to further understand energy, we have to categorize this energy. The total energy can be primarily classified into two groups, macroscopic and microscopic. Macroscopic is large-scale average values of the whole system, and microscopic is more or less the energy within the molecules. So if you look under a microscope, what is the type of energy you see there, right? Um, so macroscopic forms of energy examples are something that is usually relevant to an outside frame of reference, such as kinetic and potential energies. So if you have a bottle of water and you place that bottle of water in a very high ground, so it has gravitational potential energy, right? Now if you throw that water bottle away and it's moving fast, it has kinetic energy of the whole system. So those are macroscopic energy. And there's another one that's called pressure energy or flow energy, and it needs a little bit more defining, and we'll do that in the next few slides. Microscopic forms of energy are primarily related to molecular structure and the molecular motion. All right. and they are typically independent of outside reference frames. So let's start with the microscopic form first. So the sum of all microscopic forms of energy that are inside a system are called the inside energy or the internal energy. Okay, and it's usually referenced by the letter U. Okay, every textbook will refer it as U. Um, it includes kinetic energy and potential energy of molecules. Do not confuse that with the kinetic energy that I explained here. These are macroscopic of the whole system. Now we are talking about microscopic kinetic energy. So these are energy due to vibration of the molecules, um, energy due to rotation of the molecules, energy due to translation of molecules, um, energy due to electron translation, all the micro motion that is happening, that's the energy related to the um, kinetic motion or the kinetic energy uh, portion of the internal energy. For the potential energy portion, that is primarily due to um, the molecular forces. Okay, so the bonds and attract forces of attraction between molecules and repulsion between molecules. So those are the ones that um, contribute to the potential energy. A combination of these together um, is accounted for in the internal energy. Now, one thing to consider is there is energy, a lot of energy in the nucleus of an atom. Okay, but it is classified separately and not included in thermodynamics calculations. Okay, um, so it is beyond the scope of a thermodynamics lecture. So typically, it is not included in the internal energy calculations. Okay, so remember that for the rest of the lecture. Now, the total energy of a system on a unit mass basis is denoted by the letter small u, and it's expressed as U is U over m, where m is the mass. The distribution of internal energy between potential and kinetic is different for the three states of matter. So in solids, it's dominated by molecular forces, or potential energy is the dominant means of internal energy storage. In liquids, internal energy is stored as both potential and kinetic. So there is some molecular motion, so there is kinetic energy. In gases, there is very little intermolecular forces, so it's almost all kinetic, right? So and basically this is how these are all closely related to temperature. Now, what is total energy? So total energy is it includes both internal energy and nuclear energy along with other forms of energy. So you could start with an equation for total energy, something that looks like this, where this is the internal energy, this is the kinetic energy of the whole system, potential energy of the whole system, the pressure energy that we talked about earlier, nuclear energy, and other energies. These are the other energies are special forms of energy like magnetic, electromagnetic, surface tension, acoustic, etc. Typically, they are all neglected for most thermodynamic purposes, and nuclear energy is also neglected. Pressure energy is usually represented as pressure times volume of the system or pressure times mass divided by density. Okay, so for most thermodynamic scenarios, there is no nuclear energy or other type of energy. So this is the total energy. When we talk about total energy from now on for a thermodynamic system, you should think about this equation. Okay, so it's very confusing sometimes Like if you have to think about energy conservation, should I conserve internal energy? Should I consider conservation of enthalpy? So there are a lot of doubts that would happen if you don't fully understand where energy conservation and what is the actual total energy of the system is in a thermodynamic scenario. So this is the actual total energy. Okay. Now here you can split them into two. You can say part of it is mechanical, where there is no temperature related terms. Okay. If you look at these, it's pressure, volume energy, kinetic energy, and potential energy. You can lump them together as mechanical. And internal energy is primarily related to temperature. So you can call that as thermal. Okay. So you can say the thermodynamic total energy is a sum of thermal and mechanical energy. Now, what is the mechanical energy? If you write the kinetic energy and potential energy in terms of uh, the common equations that we normally know, uh, you will get something like this. Okay. Um, so if you remember, if you have taken a fluid mechanics class, this equation looks really familiar. If you take out the mass, it looks even more familiar. Okay, so whenever there is a conservation of mechanical energy, it is very similar to the Bernoulli's equation that you've learned in fluid mechanics. Okay, so basically it says that the kinetic energy plus the pressure volume energy, which is the flow energy or the pressure energy, plus the potential energy due to gravity in this case, uh, equals the total mechanical energy. And if the total mechanical energy is conserved, if there is no changes in mechanical energy, in Bernoulli's equation, this is conserved because there is no friction and there is no heat transfer. Okay, so when there is no friction and no heat transfer, this equation becomes Bernoulli's equation. All right. Now, pressure energy, also known as the flow energy, is the energy associated with the pressure and volume properties of a fluid or of a thermodynamic system. It's applicable to both open and closed systems, but how it is accounted for is slightly different for open versus the closed system. It's fundamentally related to work, um, but the way it is accounted for in the open system could be a little bit confusing. It's more straightforward for the closed system. So you can think of it this way. So let's say you have a system at a certain pressure and volume, okay? Now the energy that was needed to create the system and their volume was zero and you are applying a pressure, and then the amount of work needed to create a system from volume V equal to zero to a volume V equal to V, or the current volume, is the pressure energy. Okay, so basically it's this equation, 0 to V dV at constant pressure. You can also write it in terms of mass and density. Okay, so specific pressure energy would be, you will divide this by the mass and you'll get pressure over density. So that's the specific pressure energy. Now you might be confused here, but you can think of pressure as you can think of this as from another way. You know, the units of pressure is Pascal or Newton per meter square. Okay, and the unit of volume is meter cube, right? So when you multiply these two, you get Newton meter, which is similar to the unit of joules. So there's one way to remember that pressure times volume is somehow related to energy, okay? And primarily it's related to work done. If you remember from your mechanics classes that force times distance is work, right? Which is Newton times meter. So it's the same thing here, Newton meter joules, it's Instead of force, we are dividing the force per area, which is pressure. And then instead of a distance moved, it's a volume that's being displaced. So it's essentially similar, and it's a energy that's accounted for in the work term. Okay. All right. Next is the different ways of transfer of energy. Okay. So far we talked about energy. Okay. Everything here is the energy of a system. Okay. Um, and even though I said work here, a lot of times it's accounted for as an energy. Okay. And I'll clarify that in the upcoming slides. Um, because work is different from the energy of a system itself. Work is a transfer of energy. Okay. So the two different ways energy crosses the boundary of a closed system is heat and work. Okay. It can cross the boundary of an open system too, but in a closed system, there is only two ways it can cross, through heat and work, because there is no transfer of mass. So the only way energy can transfer is through heat and work. Now, how are these two distinguished? Heat is defined as the transfer that happens only if there is a temperature difference. Okay, there's a T1 and a T2 here, and the energy that crosses the boundary due to a temperature difference, even if it's a really small temperature difference, if it's caused by a temperature difference, then that energy interaction is called heat. Okay, um, so sometimes we talk about heat transfer. Heat transfer is same as heat. So essentially, based on thermodynamics definition, you don't really need to say heat transfer because heat itself is energy transfer. Okay, so it's almost like saying energy transfer, you know, due to temperature difference. But anyways, this is commonly used still, so you could refer to it as heat transfer. If you have a process where there is no energy is crossing the boundary, then it's called an adiabatic process. If you have energy transferring across the boundary, then it has to fall into, if you have heat transferring across the boundary, it has to fall into only these three mechanisms: conduction, convection, and radiation. These are the only three ways in which a delta T can drive energy transfer, or a temperature difference can drive energy transfer. Conduction is the transfer of energy from more energetic particles of a substance to the less energetic ones. Okay, um, but the main caveat here is that they should be in contact. Okay, so for a conduction to transfer energy from one object to the other, they have to be in contact. So that's one primary caveat there. So it's adjacent to the more energetic particle. So if you have a hot metal and metal 1 and it's touching a cold metal, okay, metal 2, so there will be, once they start touching, there will be heat transfer from the hot metal to the cold metal. And what essentially is happening is the atoms of the hot metal are vibrating at a much higher rate, and the cold metal the molecules are in a much lower energy state and they are not vibrating as much. But as soon as they get in contact, the vibrations gets transferred and that thermal energy is transferred to the cold metal due to physical contact. Now, if there is no physical contact, it usually gets transferred through the gases in between. Okay, so the transfer of energy between a solid surface and an adjacent fluid surface that is in motion is called convection. So it involves the combined effects of conduction and fluid motion. So because let's say you have a gas here The vibrating molecules touch the gas molecules that are adjacent to it, and then that molecule has a density difference, it moves away, and another molecule comes in. So there's motion of molecules, there's translation and vibration, motion of molecules. Okay, so when you have that kind of energy transfer, it's usually called convection. And convection itself can be natural convection or forced convection. Natural convection means the molecules are moving away only due to the buoyancy effects or the difference in density. Forced convection will be you have a fan or other means of forcing the air or the gas to move um, to increase the translational energy transfer. The third energy transfer method is the radiation, and it's due to emission of electromagnetic waves, primarily in the thermal wavelengths in the infrared region. Okay, uh, and typically this is, as you know, it is usually proportional to the temperature to the power of 4 of one body versus the other. Okay, so radiation is the other means of heat transfer, and typically the symbol used for heat transfer is Q. Do not confuse this with quality in CoolProp. Okay, Q in CoolProp. Okay, in CoolProp um, there is no function for Q for heat transfer because this is not a state function. Okay, it's a path function. The amount of energy transferred. So you cannot. So if you have a system and it's at a particular pressure and temperature, you don't know how much energy got transferred to take it to that particular state, okay? So the energy transfer that took a system from state A to state B fully depends on what path it took, okay? Was it a constant pressure process or a constant volume or a constant temperature process? It fully depends on the path that was taken. So it's a path function and it's not a property, so you cannot directly calculate Q as a property in CoolProp. And a small size Q is used to denote the specific value of the amount of heat transferred. It's joules per kilogram. All right, now let's look at work. So we already know that work and heat are the two ways of energy transfer, especially in a closed system. So if it is not conduction, convection, or radiation, and you still have energy transfer, then it's due to work. So how can you transfer energy without conduction, convection, or radiation? Well, you can do that in several different ways, and 4 different ways are shown here. One is boundary work. It's called the pressure volume work. Okay, so this is similar to the pressure energy we talked about earlier. Okay, so in closed systems, um, it is the pressure energy is actually part of the considered as work. In open systems, the pressure energy is considered part of energy. So it's a little bit confusing. So what you need to know here is in a closed system, if the boundary is moving and uh, the volume is changing, then there is work done on the system because there's something moving, okay? So the boundary is moving, so there is some work done on the system, and it's typically calculated by using this equation, integral PdV, okay? So if you know the relationship between P and V, you know the um, you know the value of integral PdV. So this relationship between P and V could be different for different processes. So the integral PDV could be a different value going from one particular pressure and volume to another particular pressure and volume. It fully depends on the path that is taken. Okay, So it is also a path function because this integral depends on the path that is taken and the type of relationship. And by path, I mean the type of relationship between P and V. Okay, so boundary work or integral PdV work is one type of work, and the other work is shaft work. So this represents boundary work because the piston is moving and changing the pressure, changing the volume. The other work is a shaft work. So if you have a rotating shaft and there's a motor outside and you're rotating and mixing this air, you're transferring some work from the motor to the inside, and it's transferred through a shaft, and it's a rotational work that's being transferred. And in this particular case, if you know the torque and the rotational speed, um, then the work done is given by this equation. Okay. You can also have another way of transferring work. So let's say you have an electrical heater inside the system and you have voltage here. You're actually increasing the temperature inside because of this. But the energy transfer is not due to the delta T. The energy transfer is due to the potential difference, right? So you're transferring energy not due to temperature difference. Uh, then the energy transferred such a way is called electrical work. Okay, so if you have a particular voltage difference V and there's a current I going inside, and the total energy that gets transferred is integrating this over time. So that will be the total work done in joules, um, by the electrical power source to on the system. Okay. And then there's other types of works like spring work. So if you have a spring and you're compressing the spring into the system, you're storing the spring energy inside the system. So that is work done on the spring, and you can typically say it is something related to the displacement of the spring. So if x1 was the initial displacement and x2 was the final displacement, then the total energy stored in the spring is that potential energy. It's actually the work done on the system if the spring is inside the system. You could The spring could also be outside the system, then the work is done by the system on the spring. Okay. All right. So just to show the path dependency of the boundary work, um, so consider this particular example. The piston moving a distance ds, then the work done is the force on the piston times the distance. That force can be converted into pressure times area times ds, and it comes to the pdv form. And now if you integrate all this small work amounts into integral pdv, you get this equation, right? The total work done. Now it fully depends on how you go from 1 to 2. So if you're taking this path versus this path, so it will be basically the area under this curve, right? So it is very dependent on the path. Okay. Now there are different relationships between P and V possible when you do an expansion or compression process of gases. Basically the pressure volume work. And typically they are represented by PV raised to n as a constant. So such process is called a polytropic process. Okay, and this n represents the polytropic index, and the c is the polytropic constant. Okay, for different types of processes, you will get different values for n and c. Now, if n equal to 1, okay, that means PV equal to constant, right? So that is, if it's an ideal gas, PV equal to nRT. So if PV is constant, then T is constant. It's isothermal process. Okay. So that's typically PV equal to constant is an isothermal process. Um, and primarily the condition there is it is an ideal gas. If N equal to 0, then P is constant. That means the pressure is constant. So that is a process like this. N equal to 1 is a process like this. So depending on the value of n, you can get the 5 standard compression and expansion processes. So they are isobaric, isochoric, basically constant volume, and adiabatic, and isentropic. So in these two cases, the n value is the same. Okay. Isentropic is an adiabatic process which is reversible. So it is almost same um, polytropic process. In this case, the n value is the ratio of specific heats, and we'll define specific heat later on. Now let's look at finding the boundary work integral for some of the common polytropic processes. Um, so if you look at the relationship, it is PV raised to the power of n is constant, right? So if what you're trying to do is an integral of PdV from a volume 1 to volume 2. Now you can replace the pressure term with Cv to the power of n and do the integral, and it will come out to be in this form. Okay. Now you have to find the value of C, which could be easily found out by substituting the initial and final pressures and volume. Okay. Um, Now, when you substitute C back into the equation, you get this particular term, which could be further factorized into this. Okay. Now choose the n for different processes that you looked at here. Um, if you choose n equal to 1 for isothermal, then the work done during either expansion or compression for isothermal process can be uh, calculated using this equation between temperature and volume, final volumes, initial and final volumes. Um, for isobaric processes, it is nothing but P times initial volume, final volume minus initial volume. For isochoric process, where there is no volume change, the work done is 0. Okay, there's no change in the boundary location. And for adiabatic processes, this is the equation for the work done. You can verify these calculations yourself when you get a chance. You don't have to memorize them, but you could use this to understand where the derivation comes from. All right. Now let's summarize what we learned so far in terms of heat and work. So heat and work are not exactly the energy of the system. They are basically describing the energy transfer in and out of the system. Okay. Um, they're both path functions in the sense that they are related to the path that the system took to reach its current state. Okay. So heat is a transfer of energy due to a temperature difference. It occurs spontaneously from a high temperature to a low temperature, typically. If the heat is added to the system, you can say the value is positive. If the heat is removed from the system, you can say that the value is negative. Now that is quite opposite for work. If the work is done on the system, it's negative. If the work is done by the system to the surroundings, then that is considered positive. Okay, and work is basically the transfer of energy due to um, anything other than a temperature difference. So it could be due to a force acting over distance. It could be due to a pressure volume work, electrical work, shaft work, spring work, etc. All right. Now let's get into the first law of thermodynamics finally. Okay. So the zeroth law we had discussed earlier. Now we are getting into the first law of thermodynamics. So far we have considered various forms of energy and energy transfer. So when we talked about energy, we talked about kinetic energy, potential energy, internal energy, all of that. And when we talked about energy transfer, we talked about heat and work. Now we tried to integrate all of that into one equation. And we'll do that for both closed system and open system. Okay. So when we do this for the closed system, the equation is typically represented in the term of internal energy. Okay, you will see that the energy equation for closed system includes internal energy. When you talk about open system, instead of internal energy, we use a term called enthalpy. All right. So what exactly is the first law of thermodynamics? It basically says that energy is conserved. Energy cannot be created or destroyed. It can change form or be transferred between systems and surroundings. Okay. For example, mechanical energy can be converted to thermal, thermal can be converted to mechanical. Energy can be transferred as work or heat from one system to surroundings. But overall, if you consider system and surroundings, the energy is conserved. Again, we are not considering nuclear energy at all. Okay. For a closed system, this energy conservation law or first law of thermodynamics essentially means that the net energy transferred to the system is equal to the change in energy of the system. So in a closed system, there is no mass going in or out, but energy can go in and energy can go out. So the net energy that is going in, okay, is equal to the change in the energy of the system. So nothing but this. Delta E system is E in minus E out. Okay. So E in minus E out includes both heat and work. So you could write E in minus E out as Q minus del W. You know that Q that is added to the system is positive and the work that is done on the system is typically considered negative. So that's why this minus sign here. So you could write E in minus E out as Q minus W. Now what is delta E system or change in the energy inside the system? You could say the total energy of the system can be expressed as sum of internal energy, pressure energy, kinetic energy, and potential energy. For a closed system, we will not use the pressure energy inside here. Okay, so remember this, otherwise it will get confusing sometimes. For a closed system, energy of the system is only internal energy, kinetic energy, and potential energy. The pressure energy is included in the work term, so it goes into this term, W. Okay, it's not included in the Q. All right, and it's usually accounted for as the pressure volume work. Okay, so E total is U plus kinetic energy plus potential energy. Kinetic energy means this closed system is moving, um, and potential energy means it's probably changing in height and gravitational potential is changing, for example. If you're talking about a static closed system where it's not moving, so the kinetic energy is negligible and the potential energy also is negligible, then you get the commonly used first law of thermodynamics for closed system, where change in the internal energy, which is the part of the delta E total, represents Q minus W. So delta E system is basically delta U system, change in internal energy, because this is negligible, this is part of the work term. So Q minus W is equal to delta U system, okay? Change in system's internal energy. So remember this equation, and whenever a lot of times, a lot of textbooks will say first law of thermodynamics energy conservation equation is this, but you have to remember it is only valid for closed systems. When it's open systems, this is not considered part of the work. This is considered part of Q, okay? And we'll get to that in a little bit. Now that we talked enough about the property of the state called internal energy, let's try to use CoolProp and start calculating internal energy and try to answer the following questions, okay? What are the internal energies of some common pure substances under standard conditions? When does a substance have zero internal energy? How does the internal energy vary with temperature at constant pressure, and vice versa? How does the internal energy of an ideal gas differ from real gas? And how does the internal energy of a liquid phase differ from the gas phase at saturation conditions? Okay. All right. So open up the thermodynamic principles Excel file and go to the UNH fluids tab. Of course, it has other properties in here too, but all I want you to look at for now is for different fluids, we are calculating internal energy values for the same temperature and pressure. Okay. And you can see different fluids have different numbers. Some of them even have negative numbers. Okay. Um, that kind of makes it confusing. How can the energy be negative? And we'll explain that in a little bit. But you can see that there's a wide range of numbers here. Some numbers are really big, some numbers are really small, some numbers are negative. Okay, and all these values are in specific energy terms. It's joules per kilogram, and the formula used is props SI, and U is the symbol for internal energy. T is one of the inputs, which is here, and I'm converting that to Kelvin. And P is the other input pressure, and that's in Pascal. Okay, and D5 is basically the name of the fluid. All right. Now, another thing of interest here is the how does the internal energy of liquids and gases compare? Okay, so for now, let's do a sorting operation here. Um, let's do a sort. And arrange them in the order of smallest to largest. Typically, you can see these liquids seems to have smaller internal energy, okay? And some of them are negative. Not all liquids. It is also dependent on the type of molecule, but typically most of the liquids seem to have lower internal energy, and the gases are the ones that are of much higher internal energy. Something to keep in mind. All right. The other thing I wanted to let you understand is why are some of the values zero? For that, you need to understand a concept, some of the values less than zero. For that, you need to understand the concept of thermodynamic reference points. So reference points serve as a baseline for defining the energy state of a substance. These points are essential because properties like internal energy and enthalpy, which you'll learn in a little bit, are measured relative to a chosen reference state. It's it's hard to um, find a state where energy is actually zero. So you basically assume that under a certain condition it's zero, and anything below that is given a negative number, and anything above that is given a positive number, and you're basically using a delta um, for calculating the energy transfer or energy changes during a process, because that's all that matters in thermodynamics, the actual change. So the origin or the reference point doesn't really matter. For example, the reference point for the internal energy of water is at 0.01 degrees C. Okay, it's a saturated liquid state at 0.01 degrees C, very close to melting or very close to freezing point of water. So at that condition, the internal energy of water is defined to be zero. So by automatically, the internal energy of ice will be in the negative, right? So there is no energy or negative energy in ice according to this definition, but it's not true, right? Of course, the molecules are moving inside ice too, but it's just a relative um, standard or relative way of calculating. And different databases use different reference points too. You know, so it's possible that you get certain internal energy for water at a particular temperature if you're using a certain database, and you'll get a different value if you use a certain other database. But the delta between two states will be same, even if the original reference points are different. Okay, so now let's look at the reference state chart here, or tab here. And you can see for three different fluids, we tried to get the internal energy close to zero. Okay, they're not exactly zero, but you can see for water, that happens at a temperature of 0.01, and the pressure is the saturation pressure for that particular temperature. Okay, so for these two conditions, water's internal energy is zero. Okay, you can use this calculation here. And for acetone, it's close to 56.15, okay, where its internal energy is zero. And for R600A, which is a refrigerant, it is at a temperature of minus 96.6. So for different fluids, the reference state is chosen differently. All right. I believe this is the boiling point of acetone, if I'm not mistaken. And for water, it's actually the freezing point. And this could be closer to the freezing point of R600A. I'm not 100% sure. But these are the values chosen, at least in CoolProp. All right. So now we have answered the question of when does the substance have zero internal energy. It's at reference points, right? Um, and how does the internal energy vary with temperature at constant pressure? So let's answer that again using the Excel file. So you can go to the U versus PNT tab, and in the beginning you have constant temperature process with different pressures. So how does the um, internal energy change when the temperature is constant? Okay, so here we have compared vapor and liquid and try to understand the internal energy change when the pressure changes. Okay, so let's first take the case of all the vapor and air. Okay, all types of vapors and gases. So in this case, we are choosing one pressure, which is the atmospheric pressure, and then we are using another pressure, which is 2000, 3000 pascals more than the atmospheric pressure. So you're choosing a higher pressure and using a temperature of 25 degrees C. So the delta P is 3000, okay? So when you do this, you're calculating U1 for P1 and U2 for P2 without changing temperature. So if you look at the equations here, U, temperature is 25 degrees C, it's converted into Kelvin. Pressure is in G9, so in column G for U1. The same equation, the pressure is basically in column H, okay? So you get two different U's, and when you look at the change is very minimal. So what does this mean? For gases, seems like pressure has little effect on internal energy, little or no effect on internal energy. Now let's consider the two vapors in here, which are water and the R600A refrigerant. And the way we have ensured that it's in the gas phase is by making sure that the pressures that we used are below their saturation pressure. So these are the saturation pressures at 25 degrees C. Okay, you can see the formula here. So these are the saturation pressure, and the way we calculate saturation pressure is by using the value Q. And I've told you before, whenever we refer to the value Q, that means we are on the saturation curve. So the P1 and P2 values are below the saturation pressures for both these cases, and they're both gases. And then we look at the U1 and U2 values at those two pressures. Here, the percentage change in delta U is still really low, but slightly more than what is there for most actual gases. So these are more like real gases, okay? And these are more like closer to ideal gases, okay? Where the internal energy change is negligible compared to pressure change, where in here, real gases, pressure change has some effect, but again, it's very minute, okay? Now, what happens when we are talking about liquids? So in case of liquids, we choose pressures above saturation pressure, and we can verify their state. Again, the internal energy change is negligible, just like ideal gases. When you're talking about um, constant temperature processes. So overall, we could say that pressure has no effect on internal energy because all these values look really tiny, okay, percentage wise. What about temperature? So consider a constant pressure process and a temperature change of, let's say, 30 degrees C. Okay, initial temperature is 25 and you're increasing the temperature by 30 degrees C. Okay, so 25 and 55. So if you look at the U1 and U2 change, that's really high, 10% change for ideal gases. Okay, it is even higher for liquids, 119 to 29% difference for liquids. And for real gases too, there is change, but it's slightly lower. Okay, so internal energy is primarily dependent on temperature. Internal energy of the system is primarily dependent on temperature. Okay, um, so that answers some of our questions that are here. How does the internal energy gets uh, affected by temperature and pressure? And we also got some answers into this. Ideal gas internal energy is more dependent on, not dependent on pressure at all, no pressure dependence at all, and slight pressure difference here. And ideal gas internal energy increases more with temperature than real gases, slightly more. Um, and we also looked at the energy of the liquid phase from the gas phase in here. Okay, so we have answered those three questions. Let's get back to the first law of thermodynamics, but this time for an open system. Again, the energy conservation essentially means the same thing. Net energy transferred to this open system uh, is equal to the change in the energy of the system. So this is the change in energy. This is the net energy transferred. Okay. In this case, the net energy transferred also includes energy due to a mass going in and out. Okay. So this is the term that is not there in the closed system equation. So there is a mass in and mass out energy term. Okay. Now at steady state, the energy in minus energy out is zero. That means there is nothing changing. A system looks like it's in steady state. So the energy going in and energy going out might balance each other at that point. So if that happens, then the equation becomes this, okay, this one. So this term is 0 at steady state. So you get this as the equation. So where did we get the Q minus W? Because those are the ways energy goes in and out. And then we have an extra term of energy going in and out due to the mass of the fluid that is going. So a certain mass of the fluid going in carries a certain amount of energy um, because of the presence of all the molecules in there. And whatever mass is coming out also has a certain amount of energy. So how is that energy accounted for? It's accounted for both by thermal, which is the U, and mechanical energy, which is all these things. You can go back in our previous slides and look at this equation from there. So there is the same terms for going in and going out, okay, but at different states. Um, However, some of the terms in this side inside this equation can be rearranged to create a new property called enthalpy. Okay, so internal energy has a clear meaning. Enthalpy doesn't have a real meaning. It is more for mathematical convenience. Okay, um, enthalpy is basically internal energy plus the PV term, which is basically this term and this term. Okay, so remember this is the basically the PV term is the work term in a closed system, but here this is part of the energy term. Okay, so U is an energy term, and uh, PV is now considered an energy term. Enthalpy is now also an energy term. Okay, so it's all part of the energy that's going in and going out. So overall, if you rewrite this equation in terms of enthalpy now, you will get Q minus W is H2 minus H1, enthalpy going out minus enthalpy coming in, plus change in kinetic energy and change in potential energy. Now, if there is no change in kinetic energy and if these values are negligible, you will get Q minus W is delta H. Okay, this is for open system. Okay, if V2, V1, Z2, Z1, all of those things are not changing much, then you get this equation. It used to be Q minus W is delta U for the closed system. Okay, so don't get confused. You have to figure out what type of system is yours, and you have to figure out when to use which equation. All right. Okay. So summarizing enthalpy, it is a thermodynamic property that represents total heat current of a system. It's usually represented by a mathematical expression U plus PV. In specific terms, it could be expressed in terms of small letters like this, okay, specific enthalpy in joules per kilogram. It is viewed as the energy required to create a system and the work needed to make space for it under constant pressure, which is the pressure energy. Okay, so um, this is the internal energy and the pressure energy. It simplifies energy balance in open systems. Okay, like turbines, compressors, heat exchangers. In refrigeration, most of the energy changes in the refrigerants are calculated by measuring the changes in enthalpy. Okay, so people by default use enthalpy, but um, it is often not understood clearly why we use enthalpy. Why do we have to always have this U plus PV term, right? But the PV term, like I said, it's coming from the pressure energy equation. And enthalpy in itself has no real meaning, but it's used for convenience. You don't have to always account for the PV term. It's a derived property for you, already calculated by the databases, so you don't have to account for the PV terms and makes the calculations easier. For processes at constant pressure, the change in enthalpy corresponds directly to heat transfer. So this is something I will have to explain here. So what that means is, suppose Q minus W um, is happening is for a closed system, okay, delta U. So in this system, you could potentially say um, work can be replaced by integral PdV. Okay, if there is no other work, it's all due to a PdV work, you can replace it like that. Now, if it's a constant pressure system, okay, in that case, it is um, integral dV is delta U, or you could say Q minus P delta V is delta U. In this case, it's clear that delta U, Q is a combination of delta U plus P delta V. This is nothing but delta H, right? Because H is PV. And if there is only constant pressure processes, then you can say that Q is delta H for a constant pressure process. So if you are talking about a closed system and you're talking about a constant pressure process, then you could directly say, you could say Q is delta U plus W, but as you could already say that Q is delta H. Okay, if you know the initial and final properties, you don't have to find the work done. You can just directly calculate the final and initial enthalpy. That will be the total Q transferred. Again, only for constant pressure processes. What is the most common constant pressure process? It's the phase change. Okay, so whenever there is a phase change, it's happening at a constant pressure. For example, if you remember the phase diagram, and its phase change is happening here at constant pressure from liquid to vapor, okay, you could basically use the enthalpy of the liquid and enthalpy of the vapor to calculate how much energy is needed to change it from liquid to vapor or vice versa. Okay, all right, and that comes from these equations. So enthalpy is used to calculate the latent heat, especially the latent heat of vaporization, okay, between liquids and gases. So the mathematical expression for latent heat is Q is equal to M times L, where L is the latent heat, Q is the total energy absorbed or released during a phase transformation, okay, and the L is the specific latent heat. It's in joules per kilogram. So if m kilograms of a substance changes from liquid to gas and L is the specific latent heat, then Q is, or the total energy absorbed for that phase change, is m times L. Now, as we just discussed, this Q is dependent on enthalpy. That means L can be calculated directly using enthalpy. Okay, so how do we do that? So the latent heat is directly related to change in enthalpy because it's defined at constant pressure. Okay, so like we just discussed, change in phase at saturation happens at a constant pressure. Okay, so you're moving from left to right or right to left. Okay, so you're the change is happening at a constant pressure, so you could use enthalpy change to calculate the total heat transfer. So the mathematical expression is HF minus HG. If you're talking about um, changing from liquid to gas. Uh, the sign could be changed depending on whether you're evaporating or condensing. Okay, HF is the specific enthalpy of the saturated liquid, and Hg is the specific enthalpy of saturated gas. Typically, Hg is much greater than HF. Okay, so the enthalpy of gas is much greater than enthalpy of liquid at the same pressure. And the difference will give you the amount of heat that you need to supply to the liquid to take the energy to a very high level close to Hg. Okay, so this is basically the equation. All right, now let's check all this out in CoolProp and verify the numbers firsthand. Okay, So the things we'll do in CoolProp are, first, we'll try to see whether is H equal to U plus PV correct? I mean, does it work for all scenarios? So we'll verify that for some of the fluids. Then we'll also check out the enthalpies of some common pure substances under standard conditions. Just like internal energy, we will check the effect of temperature and pressure on enthalpy. Um, we'll also look at the claim we just made about the differences between the liquid phase and the gas phase enthalpy at saturation conditions. We'll also do that same thing for internal energy. Then we'll try to calculate the latent heat of vaporization using the enthalpy difference, and we'll also try to see what is the internal energy change during that condition. Okay, so let's go back to the Excel file and start with the UNH fluids here. You can see that the enthalpy of all these fluids are higher than the entropy. Okay, they are larger than the entropy. Sorry, than the internal energy. That's because U is H. H is U plus PV. So you have to include the PV term to get the correct number. So for that, we'll go to this file here and we look at a standard temperature of 25 degrees C and we vary the pressures and we'll calculate the specific volume, okay, for all these gases and liquids, and we'll then multiply the pressure and the specific volume, so we have the PV term. So we have the internal energy and the PV term, okay? Then we do the U plus PV, which will be also in joules per kilogram. Then we do the actual calculation of enthalpy. Enthalpy is calculated using the symbol H, okay? And here we are using temperature and pressure to calculate enthalpy. So if you take a ratio of U plus PV that you calculate here, and then H, you can see the ratio is 1. So enthalpy is U plus PV, okay? So if you know the pressure of the um, fluid and the specific volume, and if you also know the internal energy, it's easy to calculate enthalpy, okay? So if you know P and V, you can automatically calculate U using the equations, and then using U and PV, you can calculate H. So both U and H are derived properties based on standard properties like pressure and specific volume. Okay. All right. So here we started with pressure and temperature, then we calculated specific volume, and then we used pressure and specific volume to calculate U and H. Sorry, I take that back. We used pressure and temperature again to calculate U, pressure and temperature to calculate H, U and PV, pressure and volume, to calculate U plus PV, and then these two seem to be the same number. All right. Um, so you can vary the temperature and see whether that works for any condition that you're looking for. So this is for 30 degrees C case. We could try 20 degrees C and see what happens. In all these cases, the ratio is 1. Okay. So as long as you calculate the PV correctly, U plus PV is H. So the first question is answered. And we have also looked at these numbers, and we always know that H is greater than U for all the substances because of this equation. Now, how does enthalpy vary with temperature at constant pressure? So if you remember, internal energy was only a function of temperature for most substances, right? For real gases, maybe a little bit of effect from pressure. So how does pressure and temperature affect enthalpy? For that, let's go into H versus P and T tab. So in the first case, we keep the temperature constant and vary the pressure. We change the pressure by 3000 Pascal. And we try to see what happens between H1 and H2, the two states where the pressure is changed. So you can say that enthalpy also seems like it's not getting affected much by um, pressure, except if you're close to a real vapor. For example, water and R600A, when they're close to their saturation conditions, they do have bigger um, differences in enthalpy when there is a change in pressure. Okay, it's still not too much, but we could say that only real gases have a slight dependence on pressure. Okay, like enthalpy of only real gases have slight dependence on pressure. For liquids and for real gases like air, helium, sorry, ideal gases, the dependence is very negligible. There's almost no dependence. Okay. All right. Now the next question is, what about temperature? Um, so if you look here, we are changing the temperature by 30 degrees C, T1 and T2. For liquids, there's a humongous dependence. So enthalpy changes a lot. For ideal gases also, the enthalpy change is quite significant. Um, for real gases, the enthalpy change is significant, but slightly lower than ideal gases. So strongly we could say enthalpy is primarily dependent on temperature. Okay. All right. So you could think of it in another way, because enthalpy is U plus PV, right? And U is primarily dependent on temperature, right? U is primarily dependent on temperature. And PV is, if it's an ideal gas, it's primarily nRT, or, also primarily dependent on temperature. So if the ideal gas behavior is less and it's more like a real gas, then there is pressure dependence. If it is ideal gas, then it's directly dependent on temperature. So enthalpy also is primarily a function of temperature in most ideal gas cases. Okay. All right. So what's the next question we want to answer? So we have answered these. Okay. So how does enthalpy of liquid phase differ from that of the gas phase under saturation condition? And how is the latent heat of vaporization related to enthalpy and internal energy change? Okay, for this, let's go to the HFG tab here. Okay, so here we have different fluids, water, R134A, R600A, and then we are selecting a temperature, okay, and calculating a saturation pressure for that temperature, okay. So, and then we're looking at the um, the vapor and liquid phase enthalpies and um, internal energy of these two um, phases. Okay. So for vapor, what is the enthalpy? For liquid, what is the enthalpy? The conditions are the same. These are saturation conditions. Okay. This is saturation. Okay. This 373.15 is 100 degrees C, Kelvin, um, in kelvins here. So these are the saturation conditions. For saturation condition, you can see the enthalpy of liquid is so much less than the enthalpy of gas. Okay, and the same thing goes for the internal energy. So in this case, we could look at the ratio. What is the ratio here? It's almost 6 times more than that of the liquid, okay, in that particular case. And in this case, for this particular refrigerant, it's 2 times. For this case, it's roughly 3 times. So it's usually multiple times, several 100% more uh, the energy in the vapor phase compared to that in the liquid phase. So when you have to convert a liquid to vapor, you have to use a lot of energy. So you have to use a lot of energy to boil water from water to water vapor. Okay. The same thing goes for melting ice. You have to use a lot of energy to melt ice from solid to liquid too. Okay. Now, how do we calculate the enthalpy of um, vaporization using these two numbers? It's just taking a difference between these two. Okay. So if you have to find L, which is the latent heat, all you have to do is find the difference between these two. Okay. And if you look at the difference between internal energy, that is slightly less than the difference between enthalpy. That's because the PV value for gas and liquid is different. Okay. And you know, H is U plus PV. Okay. And delta H is L is equal to H of G, is the latent heat of vaporization. So delta H is also equal to delta U plus delta of PV, right? So if you look at it that way, because delta of PV is a high number, if you look here, delta of PV is not low. Delta U is much lower than the delta H of G. Okay, even though internal energy change is huge, you have to account for a huge change in volume because the volume is increased humongously from going from vapor to liquid to vapor. So the PV term is huge. Okay, so you have to account for that. Um, so what I'm trying to get to is, imagine you have 100% heat transfer to a vessel and 100% of the heat goes to vaporize the fluid and all the liquid becomes vapor. How do we find this Q? If you thought that we have to only account for internal energy, you'll take the internal energy of this fluid initially and then the internal energy of the vapor at the same pressure and temperature of boiling. Okay, but then you'll get this number. But you'll see that you actually spend a lot more than that. You spend 225 6 kilojoules per kilogram. Okay, 2256 instead of the 2086. So how do we account for that missing 200 or so kilojoules per kilogram? That was because you also spend energy in increasing the volume, okay, of the vapor of the liquid from a small volume to a large volume. So that is the energy that you haven't accounted for here. Okay, so that's why we use enthalpy in such situations um, rather than directly looking at the change of internal energy. Okay, something to think about. And you can look at the same properties for other refrigerants here. Now, for some calculation, if you want to know the enthalpy of vaporization of any of these at a different temperature, you just change the temperature here. So I want this at -10. Okay, so it automatically calculates the enthalpy at that particular temperature. If you want it at 0, for example, and for water below 100 degrees C, what is the enthalpy of vaporization? You can get those numbers here. Okay, so that explains latent heat of vaporization and the relation to enthalpy and internal energy change. All right, so we have looked at several thermodynamic properties so far. We have looked at temperature, pressure, density, specific volume, internal energy, and enthalpy. Two other major properties are specific heat capacity at constant pressure and specific heat capacity at constant volume. Okay, so what exactly is specific heat? It is the amount of heat required per unit mass to raise the temperature by 1 degree. Okay, and it's only defined for a homogeneous phase. That means it's not defined for two phases. It's defined for a single phase, and the substance is not undergoing any change of phase. Okay, it's only defined for a single phase. Now, how is it derived? How is this property derived? We assume first law, and we assume it for a closed system. Okay, so the first law for a closed system is basically delta Q is change in internal energy plus the work done, or it used to be something like Tu is delta Q minus delta W, right? So this is the first law for a closed system. Okay. Now there are two specific heats. One is at constant volume and one is at constant pressure. So the property at constant volume, it's usually denoted by the term Cv, and the property at constant pressure, it's usually denoted by the value Cp. And if you remember the gamma value, which is the ratio of specific heats, it is the ratio of Cp over Cv. Okay, Cp is typically greater than Cv, and you will know why really soon. And the ratio is usually bigger than 1. Now, what exactly is Cv? It's a change in energy needed to raise the temperature by a small amount, okay, um, at constant volume. So you could say that the specific heat, because it's specific heat, you have to do a 1 over mass term, okay? Specific heat is the energy change per temperature change at constant volume. Okay, so if you replace the delta Q here with this equation, you have internal energy and a P delta V term inside. For constant volume, this term is 0. Okay, so basically it turns out to be change in specific internal energy over temperature, the derivative at constant volume. So that is the definition of Cv. Okay, so it's defined as a derivative of internal energy. So Cv is a derivative of internal energy that we had looked at earlier, U at constant V. Okay, so this will change based on the state of the system. This is the state property, right? So for a given temperature and pressure, you will have a certain Cv, and it will change based on the state of the system. Now, what is Cp? Cp is the same way, but done at constant pressure. So in this case, this term is not 0, okay? So, and then because P is constant, you could replace this differential as differential of U plus PV, right, at constant P. That is nothing but differential of enthalpy, because U plus PV is enthalpy, right? So this is the final formula. So Cp is nothing but derivative of enthalpy, which is H, at constant pressure. Okay, so basically when you're trying to heat a substance, okay, when you're trying to heat a substance and you put in a certain amount of Q, if you want to know how much the temperature increases, you need to know either the Cp or the Cv of that substance, depending on whether you're heating in a constant volume or you're heating in a constant pressure process where the piston moves out to keep the pressure constant. Okay, so depending on
which scenario you're talking about. Um, your temperature raise uh, temperature rise will be different, and it will be more for a CV process. For the same Q, you will have a larger temperature rise if you're heating in a constant volume, and you will have a smaller temperature rise if you're heating in a constant pressure process. You can clearly see that Cp is greater than Cv because H is greater than U, right? So the increase in H is greater than increase in U for the same um, change in temperature. So Cp is typically greater than Cv. Okay. All right. So now we should look at some other relationships between Cp and Cv. You already know that Cp over Cv is defined as gamma. Now there's another relationship between Cp and Cv, especially for ideal gases. So if you know the Cp, you can find the Cv easily. And all you have to do is, for an ideal gas, use this equation, PV equal to nRT. And if you substitute all that, you will get Cp and Cv are related by this equation, where R is the universal gas constant, 8.314. So if you're a purely ideal gas, if you know Cp, Cv is nothing but Cp minus ideal gas constant divided by the molecular weight of the gas. Okay, so it's easy to calculate one from the other if you're an ideal gas. If you're not an ideal gas, if you cannot directly use this, there will be some error if you estimate based on this relationship. All right, so now let's use CoolProp and look at both Cp and Cv calculations for some pure substances and find their standard values. Let's also make sure that this formula is correct. Verify this formula, okay, using CoolProp. And we'll also check how Cp and Cv vary with temperature. Will they increase or decrease or stay constant when the temperature is changing? Okay. All right. So let's open this Excel file and first go to the CP/Cv fluids. And here you can see the formula used. The function or the symbol is Cp mass. That's basically specifying that this is the property Cp um, defined per mass per kilogram. Okay, so the units is joules per kilogram per Kelvin, and the CV is the same. It's CV mass, and the inputs are temperature and pressure in this case. So you specify the temperature, you specify the pressure, you get CP and CV. If you take the ratio, you can see CP is always greater than CV, and the values are usually thousand. It's in the thousand orders of thousand joules per kilogram. That's the typical range of CP values for most substances, okay, per mass. Um, and if you take CP minus CV and multiply with molecular weight, you're ideally supposed to get 8.314. But most of these gases are not exactly ideal gases. So if you take helium, for example, it's very close to 8.314. Um, Water is slightly off, you know, and nitrogen is also slightly off. So you can see the non-ideal gas properties makes them slightly off from that relationship. Okay. All right. Now let's look at verify the formula Cp is dou H by dou T, or change in enthalpy, and also verify the Cv formula for air and um, for water. So in case of water vapor, so we are considering water vapor here. Um, so we find the this derivative by taking a really small delta T. Okay, so there is one temperature here and another temperature here that's just 0.001 more. Okay, so you're finding the saturation temperature, adding 5 degree Kelvin to that, and finding a delta of temperatures of 0.001. Okay, so you're taking that difference. You're calculating both the internal energy and the enthalpy at these two conditions of this temperature and this pressure. Okay, So you get CP values for those conditions directly using the CoolProp method, okay? And then you also calculate that using the differential method, okay? And you can see that if you calculate with the differential method, it's almost identical to this value, okay? So the error is almost non-existent. If you do the same thing for internal energy, there is some error, but it's not internal energy that has to be done here at constant pressure. It has to be enthalpy. So CP calculated with this formula seems to be very good with really low error. Now, constant volume process, in this case, we are calculating CV. And again, for a small delta T, this is the value here. And if you calculate it using indirectly using the derivative, using the change and the delta t, you get almost exact same number. Okay, um, very little difference. So small error. Same thing can be done for air. You can see calculated directly using the formula CP mass versus calculating the derivative, um, almost the same answer. Same thing at constant volume for CV, almost same answer. Okay, 0% error. Okay. So what this means is we have verified these two relationships to be correct using the CoolProp calculations. And we also looked at these two conditions. Now we have to look at the variation of CP and CV with temperature. So if you go back to the CP/CV fluids tab, here you can see multiple temperatures being calculated, used to calculate the CP and CV. Typically for a range from 10 degrees to 100 degrees, you can see how the CP um, varies for most gases. For helium, it's more or less constant. There's not much change. Okay. Um, and for air, there's a slight increase as the temperature goes up. For nitrogen also, there is an increase as the temperature goes up. Same for oxygen. For water, however, it decreases and then increases. So it's not um, entirely straightforward here. It first decreases and then increases from 1894 to 1891. Okay. Um, and yeah, it's somewhat similar for helium too. There's a slight reduction and it reduces even though it's almost a constant. But typically you could say that CP slightly increases with temperature for most gases. Okay, but it's not true for all gases. Same thing is true for CV. Okay, it's typically slightly increases with temperature um, and then decreasing or staying constant. So when you're trying to calculate the energy needed to raise temperature from, let's say, 10 degrees to 500 degrees, a lot of times it's okay to use a constant CP for the process, even though the CP is changing the entire time. Ideally, though, you should take an average CP of that process, like the initial and final, and then take an average CP. And it's even better if you could do an overall integral average for the whole process. Okay, so with that being said, we have looked at some of the um, main thermodynamic properties. We have understood thermodynamic states. We have looked at the zeroth law and first law of thermodynamics. One property we haven't looked at, and one of the major properties related to second law of thermodynamics is entropy, and we'll try to touch upon that in the upcoming lectures. All right, thank you.